Under a calm Atlantic sky, a cargo vessel moved at a steady pace, its steel plates humming with the same rhythm they had carried through decades of service. It had been built long before the era of container giants, in the age when shipyards still relied on riveted seams and heavy frames, and its hull carried the accumulated memory of crossings made during war and peace. Within its structure lay a reinforced compartment, designated originally as a storage hold, but engineered with specifications unlike any other section of the ship. Inside that compartment were layers of insulating material, old wiring repurposed from naval research programs, and machinery that had once been part of deep-water acoustic experiments. The ship's early life had been spent in convoy lines that stretched across the North Atlantic. It had traveled through zones patrolled by submarines, through cold layers of water where sonar signals bent and vanished, and through regions where new acoustic equipment was tested under real operational stress. During those years, it had carried an unfinished prototype of a low-frequency resonance generator, a device intended to send controlled pulses through the water column. The theory behind the device suggested that certain wavelengths could illuminate anomalies under the seabed, much as radar illuminated distant targets in the sky. Wartime engineers, still uncertain of how best to exploit underwater acoustics, used the vessel as a discrete platform for transporting and occasionally activating the system under routine cover. When peace returned, the prototype remained aboard, not because it was still needed, but because removing it was considered unnecessary work for a commercial operator. Manuals, schematics, and test logs vanished into archives, and the machinery became a dormant relic secured behind steel bulkheads. The ship's post-war crews noticed only occasional quirks, slight tremors within the aft corridor, fluctuations in compasses that settled again after a few moments, and faint mechanical tones that seemed to resonate through the hull without any clear source. These observations never amounted to more than short remarks in maintenance books. As maritime commerce grew, the vessel continued to cross the Atlantic with mixed cargoes. Its reinforced hold, the one containing the forgotten acoustic installation, was often left empty or loaded with materials that could tolerate restricted access. Stevedores occasionally remarked on the odd internal bracing, but the structure itself drew little attention. Over the years, routine inspections documented minor corrosion, old welds, and wiring so outdated that few engineers recognized its purpose. Yet the system remained intact, shielded from weather and vibration. A dormant artifact of a scientific effort few remembered. Oceanic research advanced rapidly during these decades. Underwater microphones became more sensitive, sonar pulses traveled farther, and understanding of deep sound channels improved. Oceanographers charted thermal gradients that funneled acoustic energy through layers of water, allowing sounds to propagate across great distances. Engineers learned how certain frequencies could trigger resonant effects in submerged structures. These discoveries were published in scientific journals, but none of the researchers were aware that a merchant vessel still carried an earlier, cruder version of their theoretical models hidden within its steel envelope. During an otherwise unremarkable crossing, the ship entered a region of the North Atlantic where the ocean floor descended into a broad basin flanked by submerged ridges. The sea was calm, the sky clear, and weather reports predicted no disturbances. The vessel proceeded along its usual course, engines maintaining a steady cadence, crew relaxed in the quiet routine of an uneventful passage. Yet underwater conditions were shifting in ways invisible from the deck. Temperature layers began forming a sharp boundary, creating a strong acoustic duct capable of trapping low-frequency energy. A long-range sonar test, conducted by a distant research station, sent pulses that traveled farther than intended, bending repeatedly through the layers and amplifying within the duct. As the vessel passed over the basin, stray energy from distant transmissions interacted with the dormant equipment housed in the reinforced hold. Components that had not been activated for decades responded mechanically to the frequencies permeating the hull. The device was not designed for passive resonance. Its internal frames acted like the plates of an old musical instrument, vibrating at specific intervals. These vibrations moved through the ship's structure until sensors, long unwired from any monitoring console, began to oscillate autonomously. Deep within the ship's interior, the neglected assembly started to behave as it once had during experimental tests, generating faint pulses of its own. feeding the surrounding water with low, wide-band tremors. Beneath the vessel, the seabed hosted formations that had not been charted in detail. Within the basin lay a network of geological cavities and dense mineral deposits known to produce magnetic irregularities. The region had been mentioned occasionally in oceanographic literature as a place where compasses sometimes behaved unpredictably and where sonar readings occasionally produced shadows resembling submerged ridges that did not fully align. With surveyed topography, the reactivated resonance created a column of disturbed water that reached the seabed and returned upward, forming a faint but detectable interference pattern. A passing survey ship several miles away noticed unusual echoes during its sonar routine. The operators, expecting smooth contours of the basin, instead recorded a moving irregularity as if a large mass beneath the surface were shifting position. The echo carried a signature inconsistent with submarines or whales. It appeared to rise, fade, and return on a slightly altered course. Later analysis would show that the echo aligned precisely with the position of the cargo vessel at the moment the equipment inside it began to resonate with ambient acoustic energy. On board, nothing outwardly dramatic occurred. The sea remained flat and quiet. The ship maintained speed. Yet the resonance spread through the hull, affecting metallic structures, mechanical linkages, and the thin boundary layers of water surrounding the bow and keel. Vibrations altered the reflection of sonar waves striking the vessel from below, producing a false image of a large entity occupying the same vertical plane. To distant instruments, the vessel appeared to merge with something larger and amorphous resting beneath it. The interference intensified until the ship's presence in sonar space became indistinguishable from the anomaly below. When the external acoustic field dispersed, the reflected signature collapsed abruptly. What remained for observers was an unreadable void, a patch of water where echoes did not return correctly. The vessel, though physically present, became lost to acoustic detection at the precise moment when another ship attempted to verify its position. By the time search efforts were initiated, the anomaly had dissipated. Survey ships reported only faint mismatches in bottom contours, likely artifacts of the earlier interference. No debris was found, no oil traces surfaced, and instruments detected nothing except the natural sounds of the deep basin. The cargo vessel simply failed to reappear on any form of sensor, as though it had been erased from the acoustic map of the ocean. Later reviews of its final route noted the reinforced hold, the outdated machinery, and the unusual environmental conditions that had formed during that crossing. None of these elements alone could explain the disappearance. Together they suggested a convergence of mechanical resonance, external acoustic propagation, and seabed irregularities that altered the vessel's detectability in a way not previously recorded. With no witness accounts and no radio transmissions in the final phase of the voyage, the event became another unsolved case of a ship lost in calm seas, remembered only for the strange sonar readings observed beneath it at the moment it vanished. The basin settled into its long, slow rhythms after the event, yet the water retained a subtle disturbance pattern that was not entirely natural. Marine sensors deployed over later decades picked up faint irregularities impossible to attribute to known oceanic processes. These irregularities appeared most strongly during periods when temperature gradients sharpened across the deep sound channel and when external noise diminished enough for the basin to reveal traces of its internal resonance cycle. At such times, long-range hydrophones detected ghost-like patterns oscillating far below the threshold audible to human ears, patterns whose spectral qualities resembled mechanical resonance rather than biological or geological signals. Oceanographers studying these recordings often noted that the basin acted as a partially closed acoustic system. Water masses that circulated through it entered narrow corridors structured by submerged ridges and sediment-covered plateaus. These corridors forced sound waves into layered paths, creating overlapping zones of constructive and destructive interference. Each year, as seasons changed and density fronts migrated, the geometry of the corridors shifted slightly. Such changes subtly altered the intensity and direction of low-frequency propagation. Even without the vanished vessel, the basin remained a complex resonant field, but the presence of residual patterns suggested that something had once interacted with this environment in an unusual manner. During several long-term monitoring programs carried out in later decades, researchers repeatedly encountered anomalies in the basin's deeper strata. They identified slight mismatches between predicted and measured echo returns when mapping specific sectors of the seabed. These mismatches remained stable across multiple independent surveys, each employing improving sonar technologies. The anomalies appeared as faint dimples or irregular depressions on the acoustic map. When plotted across several years, they formed a shifting mosaic of shallow acoustic shadows. None of these shadows corresponded to solid objects. Instead, they behaved like zones where reflections were subtly delayed or scattered by factors unaccounted for in standard models of seafloor acoustics. As researchers refined their instrumentation, some anomalous readings grew sharper rather than fading. Instruments with higher dynamic ranges captured subtle fluctuations in the returning signal strength. The viewers watching real-time sonograms observed fleeting distortions that formed and dissolved in patterns too complex to resemble ordinary clutter. Attempts to model these patterns mathematically yielded results suggesting the influence of resonant cavities beneath the seabed. The suspected cavities were not uniform voids, but irregular structures, possibly filled with compacted sediments or layers of hardened mineral deposits. Such features could reshape passing sound waves in unpredictable ways, generating pockets of interference capable of masking or distorting the presence of large submerged objects. Submersible expeditions considered exploring the basin, but the combination of great depth, unpredictable acoustic conditions, and the absence of clear geological targets discouraged most attempts. Funding was instead directed toward more accessible regions displaying hydrothermal activity or tectonic movement. As a result, the basin remained largely unvisited by modern submersibles, and human eyes never directly observed the irregularities that consistently appeared in sonar records. Despite the lack of direct exploration, the basin continued to enter academic discussions about marine acoustics as an example of a natural environment capable of amplifying certain frequencies to an unusual degree. Over time, as sonar technology evolved, the basin became an accidental case study in long-term acoustic anomalies. Vessels passing dozens of miles away occasionally reported mild disruptions to their navigation systems. These disruptions manifested as temporary compass deviations, slight offsets in inertial navigation calculations, or inconsistent depth readings. Though each individual report was too minor to attract attention, compiled records formed a subtle pattern. Most of these deviations occurred along travel lanes, intersecting the outer regions of the basin. Engineers reviewing the reports proposed that the anomalies resulted from small but persistent magnetic irregularities produced by mineral-rich formations in the seabed. However, these explanations did not fully align with the data. The deviations tended to appear during periods when the basin's internal temperature structure indicated heightened acoustic reflectivity, suggesting that the phenomena might be connected to sound propagation rather than magnetic disturbances. Such ideas gained traction when comparative studies showed that low-frequency tones recorded near the basin shared a faint but consistent harmonic pattern. This pattern echoed the spectral signature once generated by early experimental resonance devices. Analysis indicated that the signature was not stable but drifted slowly across a narrow frequency range, influenced by seasonal shifts in water density. Some researchers proposed that remnants of the vanished ship's resonance could still be circulating through the basin, trapped within a layered structure that allowed acoustic energy to persist far longer than expected. Their papers noted that certain natural environments acted as storage chambers for sound, preserving and slowly re-emitting energy introduced by mechanical sources. Examples included deep fjords, submarine canyons, and enclosed basins insulated from strong mixing currents. The idea that the vanished vessel had imparted a long-lasting acoustic imprint became a subject of niche debate within marine physics circles. Some researchers suggested that the mechanism inside the ship could have generated pulses powerful enough to interact with natural structures beneath the basin. If those pulses coincided with particular phases of the basin's internal oscillation cycle, the convergence might have produced a self-reinforcing resonance lasting well beyond the initial event. Although these theories remain speculative, They gained support from data showing that certain anomalies exhibited recurrence intervals matching the approximate oscillatory period of the basin's water masses. As decades progressed, improvements in underwater listening systems revealed additional nuances. Arrays of sensors positioned thousands of miles apart detected faint, intermittent bursts of low-frequency noise originating from the general direction of the basin. These bursts were not strong enough to travel great distances on their own. Instead, they likely rode along the deep sound channel, which acted as a natural waveguide. The deep sound channel allowed them to propagate with minimal energy loss, enabling their detection far beyond the basin's boundaries. Analysis of these signals showed that they did not match known biological calls, geological tremors, or anthropogenic sources such as ship engines. Instead, their spectra contained irregular harmonics, characteristic of decaying resonance. Oceanographers attempted to correlate the bursts with seismic activity and tidal cycles, but found no consistent links. Some of the bursts appeared during completely stable conditions, suggesting an internal trigger within the basin. Others occurred immediately after long periods of silence, hinting that the basin might accumulate acoustic energy until it reached a threshold, then release it in sudden diffuse pulses. Such behavior resembled the dynamics of certain resonant mechanical systems, though the scale and mechanism remained unknown. The notion that a vanished vessel had initiated this cycle remained unproven, but difficult to dismiss entirely. The basin's influence extended beyond acoustics. Over the years, surface vessels passing near its perimeter occasionally reported encountering patches of water with unusual temperature gradients. These gradients sometimes formed thin, horizontal layers, only a few meters thick but extending over considerable distances. Within such layers, sound waves could travel with altered velocity, complicating depth measurements and creating false bottom echoes. Mariners described brief moments when instruments indicated rising seafloors where none existed, only for the readings to stabilize moments later. These episodes were often accompanied by patches of water unnaturally still compared to the surrounding sea, as though surface ripples had been dampened by an invisible boundary. Remote sensing from satellites eventually revealed slight discrepancies in sea surface height over parts of the basin. These discrepancies were too small to be noticed by the naked eye, but significant enough to appear in sensitive altimetric data. They suggested minute variations in density below, possibly caused by slow changes in temperature structure or the presence of concealed geological formations. When combined with acoustic data, these clues supported the idea that the basin possessed a layered architecture more complex than initial surveys suggested. In academic circles, the region gradually gained a quiet reputation as a site where instruments behaved unpredictably. Although it never attracted the sensationalism associated with maritime myths, researchers increasingly treated it as a genuine scientific curiosity. Papers describing minor anomalies often reference the basin as an example of how natural acoustic systems could mimic or obscure the presence of man-made objects. Occasionally, a researcher revisiting the historical record would note the coincidence of the vessel's disappearance with a period of heightened acoustic activity in the area. While no definitive link could be established, the event remained a foundational reference point for discussions about environmental resonance effects and their impact on underwater detection. Across the decades, the basin kept its quiet rhythms, releasing periodic traces of energy into surrounding waters. Subtle, persistent, and ambiguous, these traces formed a thread connecting the vanished vessel to the evolving knowledge of the deep ocean. The ship itself remained unfound, its final location unknown, its structure possibly intact somewhere within the basin's layered depths, concealed by the same acoustic distortions that once masked its presence during the search. If the hull still existed, it lay beyond the reach of ordinary detection, caught within a complex interplay of resonance, geology, and fluid dynamics that ensured its silence. The basin's deeper levels evolved over time, shaped by subtle geological and hydrodynamic processes that unfolded too slowly for any single generation to observe directly. Sediments descended through the water column in a continuous drift, accumulating in layers that reflected changes in climate, plankton distribution, and ocean currents. Each layer, no thicker than a sheet of paper, added to the stratified structure of the seabed. Over decades, these layers shifted the acoustic properties of the region, forming new lenses of compacted material that refracted sound differently from the looser sediments above them. The entire basin became an archive of environmental history, preserving faint hints of past events, including the one involving the vanished vessel. As the sediment layers grew thicker, they buried older features, while revealing new ones. Acoustic surveys conducted long after the disappearance indicated that portions of the basin floor possessed irregular densities. Some areas appeared unexpectedly rigid, suggesting underlying mineral formations shaped by ancient tectonic processes. Others displayed softer, more porous qualities, as though the seabed concealed labyrinths of interconnected voids. These voids, though invisible to most sonar frequencies, influence the return patterns of certain deep penetrating pulses. When the pulses encountered hidden pockets of low-density material, they scattered in unpredictable directions, adding to the complexity of the basin's acoustic profile. In this layered environment, the remnants of the vessel, if they still existed, would have become progressively harder to distinguish from their surroundings. The hull, once a coherent, reflective body, would gradually lose its structural identity as sediments accumulated around it. Metallic surfaces, exposed for years to slow-moving currents and fine deposits, would begin to blend into the seabed, their contours softened by corrosion and burial. Marine life colonizing the area would further accelerate the process, covering any exposed surfaces with layers of organic material. Over time, the vessel's acoustic signature would weaken until it matched the ambient reflections produced by the basin's geological features. Marine organisms introduce their own contributions to the acoustic environment. Every deep basin hosts ecosystems adapted to low light, low temperature, and high pressure. In this particular basin, certain species generated faint biogenic noises, pulses, and vibrations produced during feeding or movement. Although these signals were extremely weak, they occasionally synchronized in ways that mimicked larger disturbances. Researchers analyzing long-term recordings sometimes observed clusters of such signals merging into composite patterns. These patterns, when filtered incorrectly, resembled the decaying harmonics of low-frequency mechanical devices. The presence of these biological signatures complicated attempts to isolate any trace of the vanished vessel's resonance. Meanwhile, the upper layers of the basin continued to interact with large-scale ocean dynamics. Seasonal changes in surface heating created shifting thermoclines, zones of abrupt temperature change that functioned as acoustic mirrors. When a thermocline descended into alignment with deeper density layers, sound waves entering the basin could be trapped within a vertical corridor. This corridor acted as a conduit for distant noise, allowing external sounds to penetrate deeply and sometimes re-energize dormant resonance patterns within the basin. The effect was akin to striking a long, silent instrument with a faint echo of its original tone. On rare occasions, instruments detected the re-emergence of harmonic structures similar to those produced decades earlier, though these reappearances were always brief and unpredictable. In later decades, advanced hydrophones were deployed across the ocean as part of global monitoring networks. These networks captured wideband acoustic data from multiple basins, including the one associated with the disappearance. With increased sensitivity, researchers observed anomalies that had previously gone unnoticed. Some of these anomalies traced back to the basin's perimeter, forming weak but consistent signatures. When plotted over time, the signatures formed a diffuse halo around the region, as if the basin emitted faint pulses at irregular intervals. Attempts to trace these pulses to geological or biological sources yielded inconclusive results. Long-range modeling showed that the basin possessed a unique combination of characteristics: a complex seabed geometry, stratified sediments, layered water masses, and a deep sound channel intersecting with older geological formations. This combination created conditions ideal for storing, transforming, and re-emitting acoustic energy. Researchers concluded that the basin might function as a vast, slowly oscillating resonant structure shaped not by engineering but by geology and oceanography. In such a structure, any external acoustic event from storms to mechanical noise could imprint itself upon the basin, leaving behind echoes that persisted far longer than expected. Under this interpretation, the vessel's disappearance could be viewed not as an isolated anomaly, but as the beginning of a long-term interaction between the ship's internal resonance and the basin's natural acoustic properties. The ship, carrying an outdated low-frequency generator, might have triggered a feedback loop within the basin. If the basin amplified certain frequencies and the vessel responded to those frequencies, the interaction could have intensified rapidly, creating interference patterns that masked the ship from detection. The ship may have remained physically intact, but acoustically invisible, merged into the basin's resonant field. Years later, when more advanced instruments tried to detect structures within the basin, they encountered only shifting patterns of interference that blurred the boundary between solid objects and acoustic shadows. The consistent failure to locate the vessel's remains suggested that its physical presence no longer created a discernible echo. Either the ship had been buried under tons of sediment, or the geological complexity of the basin rendered it indistinguishable from natural formations. In either case, the vessel became part of the basin's long, slow evolution. Some researchers studying the region saw parallels with other deep marine basins known to generate persistent, low-frequency phenomena. These basins sometimes emitted tones resembling distant machinery, even when no anthropogenic sources were nearby. Theories suggested that shifting water masses moving across submerged ridges produced harmonic vibrations. Others believed that certain geological formations acted like resonant plates, converting internal stresses into audible frequencies. Such natural mechanisms varied widely from one basin to another, and in each case, they produced unique acoustic fingerprints. The basin in question exhibited this behavior to an unusual degree, making it difficult to distinguish natural signals from those that might have originated from the vessel. Over time, speculative hypotheses emerged, proposing that the ship itself might still lie somewhere within the basin, preserved in fragments or partially intact. According to this view, the vessel had not been destroyed but had merely become acoustically indistinct. Its hull, once capable of reflecting sonar clearly, would have lost this property as sediments accumulated and corrosion progressed. The ship's structure might still exist beneath layers of silt and debris, camouflaged by the basin's evolving acoustic environment. Even if the hull had collapsed, remnants of the acoustic device might persist. Metal frames, reinforced plates, and vibration-damping components could remain embedded deep beneath the seabed. These remnants would not reflect sound strongly. Instead, they might contribute to the basin's overall acoustic interference pattern. Their presence could explain the faint harmonic structures that re-emerged occasionally, long after the initial event. Understanding the basin's dynamics required considering the slow interplay between geology, water chemistry, and acoustic energy. The seabed's sediment layers thickened by fractions of millimeters each year. Cold currents entering the basin pushed deeper layers downward, compressing older sediments into denser forms. As density increased, the acoustic impedance of buried structures changed, altering how sound waves passed through them. A metal hull buried beneath such layers could eventually become virtually transparent to certain sonar frequencies, blending seamlessly into the background. Through all these processes, the ocean maintained its silence. The basin continued to shift, reshape, and oscillate. Each decade added new layers of complexity to its acoustic profile, while older layers settled into deeper, colder strata. Whatever had happened to the vessel, its story became part of the basin's expanding history, preserved only in faint, decaying echoes. As the decades advanced, the basin's internal structure matured into a layered acoustic labyrinth shaped by sedimentation, subtle tectonic compression, and the relentless movement of abyssal water masses. Within these depths, acoustic energy behaved in ways that no surface observer could have anticipated. Hydrographic data collected much later revealed that the basin acted not merely as a passive receiver of sound, but as an active modifier, bending, warping, storing, and gradually re-emitting frequencies introduced into it across spans of time longer than the lifespan of any vessel crossing overhead. The density gradients between layers thickened incrementally year after year, their boundaries sharpening into narrow, lens-like planes that redirected incoming sound waves into spiraling trajectories. Even a minor fluctuation in the temperature profile could transform these acoustic lenses, rendering the basin an ever-changing continuum where sound traveled not in predictable arcs but in recursive folding patterns. These transformations were unnoticed in the mid-century years following the vessel's disappearance, because the tools capable of revealing them did not yet exist. Maritime operations depended on sonar systems with limited resolution and narrow frequency windows. blind to the deep structural complexities that shape the basin's internal acoustics. As a result, when ships passed overhead and noticed sudden fluctuations in depth readings or brief compass irregularities, the anomalies were attributed to equipment errors or momentary magnetic distortions rather than the basin itself. In truth, the navigation systems of those vessels had brushed against a region where natural resonances built up over decades momentarily interfered with their instruments. These effects were so brief and subtle that they passed without record, but the basin remained in a perpetual state of slow acoustic oscillation, accumulating faint echoes of long-past events, including the resonance triggered by the vanished cargo ship. Sediment deposition proceeded at its usual glacial pace, but the structural changes it introduced were cumulative and profound. Each new layer compacted the strata below it, pushing older material into greater density and altering its ability to transmit or resist acoustic penetration. The seabed within the basin was far from uniform. Beneath the uppermost layers lay a complex mosaic of hardened silt, mineral-rich patches, dense clay pockets, and microcavities formed by ancient geological processes. These microcavities, some no larger than a human fist and others extending several meters, created chaotic scattering fields where incoming low-frequency waves refracted unpredictably. Over long periods, these scattering fields absorbed and diffused sound energy into intricate patterns, some of which persisted in weakened form long after their initial source had vanished. If the vessel's hull had settled within this environment, whether intact or fractured, it would have become enveloped by layers of sediment that grew thicker and more compacted with each passing year. The metal plating, once a strong reflector of sonar pulses, would have lost its acoustic contrast against the surrounding material as sediments encased it and corrosion thinned its structure. Different metals corroded at different rates, producing irregularities that further blended the ship's signature into the complex acoustic tapestry of the basin. The resonant qualities of the reinforced hold, once capable of sustaining mechanical oscillations, would have decayed until the cavity no longer responded to external frequencies. Whatever remained of the internal machinery, the frames, mounts, wiring, and plates of the abandoned acoustic device would have experienced the same fate, becoming a buried and acoustically muted remnant. Changes in the basin were not limited to geology and sedimentation. Abyssal currents, though slow, continually transported cold, oxygen-poor water into the deepest recesses, where it accumulated in sluggish pools whose boundaries shifted only with substantial climatic changes. These pools served as reservoirs of acoustic energy, trapping low-frequency waves within their boundaries for extended periods. When external conditions altered the density structure above them, these pools sometimes released stored energy in faint pulses that ascended through the layered water column. Hydrophones capturing these pulses decades later interpreted them as ghost signatures, weak, fragmentary echoes resembling attenuated copies of older signals. In some cases, the spectral form of these pulses bore a faint resemblance to the decaying harmonic pattern associated with early experimental resonance generators, including those used aboard the vanished cargo vessel. Whether this resemblance was coincidence or a lingering imprint transferred into the basin during the event remained impossible to prove. Meanwhile, global ocean monitoring projects expanded, collecting vast archives of acoustic data. As more permanent hydrophone arrays were installed in the deep ocean to monitor seismic activity, whale migrations, and submarine movements, the basin's peculiar acoustic behavior became more apparent. Across different arrays positioned thousands of miles apart, analysts noticed intermittent bursts of energy arriving with timing that suggested a common distant source. These bursts were extraordinarily faint and of low frequency, occupying a band where only large-scale natural events or specialized mechanical sources typically operated. Time correlation indicated that the signals traveled via the deep sound channel, that natural underwater waveguide, capable of carrying sound to distant regions with minimal attenuation. When researchers traced the origin of these bursts, the triangulation repeatedly led to the general region of the basin. Yet surveys conducted during the same periods revealed no seismic events, no military experiments, and no significant marine disturbances that could explain the phenomena. The bursts lacked the uniform spectral characteristics of biological calls and did not match the signature patterns of tectonic activity. Instead, the signals displayed a drifting harmonic structure, as if influenced by slowly changing environmental conditions. Researchers trying to identify the cause proposed that the basin itself, because of its layered sediment structure, submerged cavities, and interaction with the deep sound channel, might intermittently re-emit acoustic energy previously absorbed from external or internal sources. The idea of the basin functioning as a form of natural acoustic storage chamber was controversial, but not without precedent. Similar behaviors had been documented in deep fjords, karst underwater caverns, and certain polar basins where dense water layers trap sound for extended periods. In those environments, low-frequency signals sometimes resurfaced long after the initial sound had dissipated. The basin associated with the vessel's disappearance exhibited analogous characteristics, though on a larger scale and with far more complex interference patterns. The notion that the vanished ship's resonance device might have contributed energy to this system remained speculative yet plausible, given the unique conditions present during the disappearance. Oceanographers studying long-term temperature cycles noticed that certain anomalies occurred during intervals when water stratification intensified. During those periods, the basin appeared acoustically tighter, with fewer paths for sound to escape and greater amplification within specific layers. These intervals often coincided with slight increases in the number of anomalous bursts detected by distant hydrophones. Though correlation did not imply causation, the patterns suggested a link between the basin's internal structure and the occasional resurgence of low-frequency energy. No human had ever directly observed the basin's deepest regions. Submersible vehicles rarely ventured into the area because of its depth, remoteness, and lack of obvious scientific targets compared to geothermal vents or tectonic ridges. Exploratory missions tended to favor regions with active processes rather than quiet basins that appeared static in satellite and surface scans. Thus, the basin remained a blind spot on the oceanographic map, a place studied primarily through indirect measurements. Without direct visual confirmation, any speculation regarding the physical fate of the vessel remained unverified and likely to stay unanswered indefinitely. Navigation records from vessels passing near the basin over the decades revealed occasional but consistent deviations. Some of the deviations appeared in compass logs, others in depth recordings, others still in inertial navigation data. The deviations were weak, often lasting only seconds, but their recurring nature suggested an underlying environmental influence rather than random error. When plotted spatially, the deviations formed a halo-shaped zone extending outward from the center of the basin. In this halo, navigation instruments behaved with slight irregularity that reversed once the vessels moved beyond the region. Engineers theorized that subtle magnetic variations in the seabed's mineral structures contributed to the anomalies. But the timing and intensity of these deviations matched too neatly with periods of acoustic interference documented in the basin, suggesting a more complex phenomenon where acoustic and electromagnetic effects intertwined. Throughout this period, the location where the vessel likely settled remained acoustically concealed. Even with modern sonar capable of high-resolution mapping, the basin resisted full analysis. Sonar beams entering its deeper layers often returned distorted or scattered signals, producing blurry or ambiguous images of the seabed. Some surveys identified elongated shadows that could have indicated a partially buried object, but subsequent scans failed to reproduce the contours. The variable propagation of sound within the basin made consistency impossible. A structure, if present, could appear, disappear, and reappear depending on water temperature, salinity, stratification, and the configuration of sediment layers on any given day. The absence of definitive sonar images prompted discussions about acoustic invisibility, a term typically used in theoretical studies of how objects could be shielded from detection by manipulating surrounding media. In this naturally occurring environment, something similar seemed possible. An object, once enveloped by sediment, and submerged beneath layers that altered acoustic impedance, could effectively vanish from all but the most penetrating frequencies, and even those frequencies might be scattered by the basin's intricate internal geometry. If the vessel remained there, Its ghostly invisibility was not the result of intentional concealment, but of the basin's relentless evolution. The basin entered a phase of long-term transformation that unfolded across decades, shaping the hidden environment where the vanished vessel might still rest beneath accumulating sediments. With each passing year, the deep ocean's relentless processes altered the region's physical and acoustic identity. The abyssal waters circulating through the basin moved in slow, spiraling patterns, transferring heat, salts, and microscopic particles between layers. These spirals operated on timescales far longer than human lifetimes, completing full cycles only after many decades. In the slow churn of those deep currents, temperature gradients thickened and sharpened, forming vertical corridors of sound guidance and horizontal barriers that redirected energy in looping courses. The water masses that flowed into the basin from the surrounding abyss carried with them faint background noise, distant echoes of storms, calving icebergs, undersea landslides, and the vast chorus of marine life. But once these waves reached the basin's inner layers, they lost their identity, bending into patterns dictated by the basin's shifting density features. Sedimentation proceeded with deceptive calm. To an observer watching for only a few hours or even a few weeks, nothing would have seemed to change. Yet over longer intervals, the slow rain of organic debris, detrital grains, mineral dust, and microscopic shells accumulated into layers measurable only when viewed across decades. The layers nearest the surface remained soft, porous, and water-rich, but deeper strata compacted under their own weight until they hardened into dense, laminated structures capable of reflecting or absorbing sound in unusual ways. Within those layers were embedded the histories of storms, plankton blooms, volcanic ash fallout from distant eruptions, and even rare atmospheric anomalies that rained particulates into the ocean. These records formed a geological archive across the seabed that grew thicker, heavier, and more acoustically complex with each passing year. If parts of the vessel had settled into this environment shortly after its disappearance, they would have been surrounded by sediment grains so small as to be carried easily in the quiet currents of the deep. These grains, accumulating in slow layers, would gradually enclose the hull. The metal surface's iron, steel, copper alloys would react chemically with the cold, oxygen-poor water, undergoing slow but steady corrosion. Over decades, the sharp lines of the hull would soften, edges would crumble, and surfaces would become pitted and roughened. As corrosion advanced and sediments accumulated, the acoustic reflectivity of the vessel's surfaces would diminish until they matched that of the surrounding deposits. In time, even a high-powered sonar pulse would fail to differentiate between the decaying hull and the seabed itself. Below the sediment layers lay the underlying geology of the basin, formed over millions of years. The region contained compressed mineral beds and fractured basaltic structures shaped by ancient tectonic forces. Some sections of the seabed exhibited unusual density contrasts, sharply defined boundaries between compacted clay and rigid rock, porous pockets surrounded by harder mineral shells, and layers of sedimentary debris distorted by long-past landslides. These irregularities, though invisible to surface observers, created scattered fields for sound waves that passed through them. Low-frequency pulses entering these structures would be split, refracted, delayed, or redirected in complex ways. As the basin evolved, these geological features became increasingly pronounced, enhancing the environment's ability to modify and re-emit distant sounds. In deeper pockets of the basin, water masses occasionally formed stable pools whose temperatures and salinity levels remained virtually unchanged for years. These pockets acted as temporary storage chambers for low-frequency energy, trapping faint signals broadcast from storms, seismic events, or passing whales. When the density structure of the basin shifted due to seasonal cooling at the surface or long-term oscillations in ocean circulation, these trapped pockets released their stored energy in weak pulses that ascended through the water. Column hydrophones placed far from the basin detected these pulses as long, drifting tonal signatures, whose origins could not be clearly identified. Analysts who conducted retrospective studies decades later noticed that some of these pulses bore spectral characteristics remarkably similar to the early resonance devices used during mid-century research programs. Whether this resemblance reflected a lingering imprint from the vanished cargo vessel's internal machinery remained a matter of speculation. The oceanographic community only became aware of the basin's peculiar acoustic behavior when global monitoring networks expanded. The deployment of long-range hydrophone arrays, originally intended to detect nuclear tests and monitor submarine movements, inadvertently captured years of acoustic data from the basin region. Analysts noticed sporadic bursts of low-frequency noise arriving along the deep sound channel, that natural waveguide that allowed sound to travel vast distances with little loss. When these bursts were triangulated, their point of origin consistently fell near the basin. Yet no known tectonic activity or anthropogenic operations corresponded to the bursts. Biological explanations failed as well. The frequency structures did not match any known vocalizations of deep-diving whales or large marine mammals. The signals drifted slowly in frequency over time, consistent with the influence of moving thermoclines or shifting density gradients, rather than an active biological source. These findings prompted a series of studies investigating the basin's internal acoustics. Researchers compiled decades' worth of sonar logs, temperature profiles, and hydrographic surveys, uncovering patterns no one had previously recognized. The basin's stratification fluctuated periodically, almost rhythmically, in ways that subtly modified the paths available for sound propagation. During periods of strong stratification, sonar pulses entering the basin became trapped in horizontal layers, traveling in long loops before dissipating. In periods of weaker stratification, sound penetrated deeper into the sediments, interacting with older geological layers that imparted unique phase shifts. These complex propagation characteristics made the basin a place where sound could vanish, re-emerge, or transform unpredictably. Navigation records from commercial ships passing over or near the basin added another layer of evidence. Some vessels reported brief, unexplained deviations in compass headings or depth readings. Others experienced transient disruptions in early inertial navigation systems, which at the time were sensitive to even minor anomalies in gravitational or magnetic fields. None of these deviations were strong enough to cause alarm, but when examined collectively, they revealed a pattern. The anomalies most often occurred when ships crossed a halo-shaped zone surrounding the basin's center. Instrumentation errors disappeared once vessels traveled beyond that zone, suggesting an environmental cause localized within a narrow area. Engineers initially suspected magnetic variations caused by mineral deposits in the seabed, but the timing and distribution of the anomalies aligned too closely with the basin's internal acoustic events for the magnetism explanation to stand alone. As sonar technology improved, oceanographers attempted to map the basin with ever-increasing resolution. However, the deeper layers resisted clear imaging. High-powered sonar pulses that should have penetrated the sediments returned distorted echoes, or none at all. Structures appeared one year and vanished the next. Apparent ridges dissolved into ambiguity when scanned at different frequencies. Some surveys detected elongated shadows, consistent with a large, partially buried object, but repeat surveys failed to confirm their existence. The basin acted as an acoustic chameleon, altering its reflective properties based on conditions that were impossible to measure directly. A structure, if present, could be rendered invisible simply by a slight shift in water density or a minor change in the composition of overlying sediments. This phenomenon led to discussions of natural acoustic cloaking, a concept also explored in theoretical physics. In controlled laboratory environments, researchers had demonstrated that certain materials could bend sound waves around objects, rendering them undetectable to specific frequencies. The basin appeared to replicate similar conditions on a massive scale. Its stratified layers, irregular geological features, and deep sediment deposits created pathways for sound to travel around buried structures rather than reflect from them. Consequently, an object concealed beneath the sediment could become effectively acoustically transparent, no more detectable than the surrounding environment. Over time, the basin's acoustic behavior became the subject of deeper research. Scientists studying global ocean noise observed that the basin contributed faint but measurable signals to the deep sound channel that spanned thousands of miles. These signals were too weak to be recognized individually, but statistical analysis revealed their persistent presence. The signals fluctuated in frequency over long timescales, drifting according to changes in the basin's stratification. Occasionally, they intensified, forming pulses that traveled outward like ripples. But these pulses bore no signatures of seismic events or biological calls. Instead, they resembled the decaying harmonics of long-lived resonance, gradually fading before rising again in modified form. The possibility emerged that the vanished vessel, or the acoustic device it once carried, had introduced a form of energy into the basin that the environment continued to recycle. Even if the device had ceased functioning long ago, the basin's unique properties might have stored and transformed its original output into long-lasting patterns. This concept was speculative but compelling, given how natural systems sometimes sustain disturbances like vortices in fluid dynamics that persisted far longer than expected. The basin, with its intricate geometry and layered structure, might serve a similar role for sound, a medium in which frequencies introduced decades earlier continued to circulate in attenuated form. Without direct exploration, the fate of the vessel remained unresolved. If the hull lay buried deep beneath sediments, the basin's evolving layers would continually further obscure it. If the metal had broken into fragments, those fragments would scatter and settle within geological depressions, each piece undergoing corrosion until it blended seamlessly with mineral deposits. The reinforced hold, once the resonant core of the vessel's acoustic behavior, might remain recognizable only as irregularly shaped pockets of compacted debris embedded within hardened strata. The ocean itself offered no clues. Surface conditions above the basin remained calm, giving no indication of the intricate and hidden dynamics unfolding below. Waves passed overhead without witnessing the slow interplay of acoustic fields, sediment layers, and geological structures. The surface water, far removed from the basin's depths, responded only to wind and weather, showing nothing of the deep cycles that occasionally produced faint echoes traveling along the deep sound channel. In the end, the basin became not merely the site of the vessel's disappearance, but an autonomous system shaped by its own deep history. An environment where sound lingered, sediments grew, and geological layers shifted slowly over time. Whatever had happened to the vessel seemed less like an isolated event and more like a convergence of natural forces. A moment when unique conditions briefly aligned to obscure a large object from detection and gradually absorb it into the basin's evolving structure. The ship, once a visible and functional part of human maritime activity, now existed only as a faint suggestion within the complex acoustic profile of the basin. As global observation systems became more sophisticated, the basin's subtle influence began appearing in places and data sets that had never originally been designed to capture it. Long-range acoustic networks, installed across the oceans to monitor seismicity, marine life, and anthropogenic noise, repeatedly flagged stretches of data containing faint, slowly drifting bands of energy whose source, when triangulated, traced back to the same coordinates. These bands did not behave like ordinary propagating waves. They appeared as quasi-stationary features in frequency space, shifting gradually across weeks or months, as if the basin's internal structure were slowly tuning itself. When displayed as spectrograms, they resembled narrow, meandering trails of intensity wandering through the low-frequency domain, often crossing the boundaries between bands associated with known ambient noise. Researchers who specialized in background ocean noise began treating the basin as a natural laboratory in which to study how complex stratified environments could shape and store acoustic energy. They noted that the basin's signature did not present itself as a distinct tone, like the distant hum of a machine, but as a persistent deformation of the normal noise field. Wherever the basin's influence extended along the deep sound channel, the usual blend of wind-driven, shipping, and biological sounds acquired a subtle asymmetry. Certain frequency ranges seemed selectively emphasized or suppressed, and the overall statistical distribution of amplitudes skewed slightly from the global average. Such deviations were too small to notice in isolation, but by comparing multi-year data sets across many regions, analysts could see that the sector connected to the basin departed systematically from expected patterns. As the observational record lengthened, the basin's behavior began to suggest that it was following a very slow cycle. The spacing and intensity of the anomalous bursts, the timing of navigation irregularities, and the frequency with which deep sound channel signals carried traceable distortions all appeared to wax and wane over intervals of several decades. Numerical models that coupled ocean circulation, sediment compaction, and acoustic propagation hinted that the basin might support large-scale standing modes of low-frequency energy, whose periods were tied to the turnover times of abyssal water and the rates of vertical heat exchange between deep layers and the overlying ocean. In these models, the basin acted like a vast, three-dimensional resonator, whose geometry changed so slowly that its natural notes drifted almost imperceptibly over human timescales. Into this evolving structure, the vanished ship's resonance had once been introduced as a brief, sharp excitation. The event did not create the basin's acoustic capacity. It merely illuminated it, injecting mechanical energy at precisely the frequencies the environment was best suited to store. Decades after the last crew list of the missing ship had faded from memory, its echoes literally and figuratively still circulated. In one global analysis, researchers cross-correlated recordings of the basin's low-frequency anomalies with records of distant storms, submarine landslides, and polar ice calving. They discovered that certain extreme events, when their acoustic fronts intersected the basin at appropriate angles and phases, could temporarily re-energize modes that had lain dormant for years. In these moments, the basin briefly amplified the external disturbances, reshaping them into characteristic patterns before releasing them into the deep sound channel as faint, modified pulses. No single pulse carried a recognizable fingerprint of the long-vanished generator or its host vessel. Yet in aggregate, the basin's behavior bore the unmistakable mark of having once been driven strongly at a particular combination of frequencies, much as a struck bell retains minute structural changes in its metal long after the initial impact has faded. As theoretical work advanced, some groups began to view the basin not just as a complicated acoustic environment, but as part of a larger class of geophysical memory structures scattered across the planet. These were places where physical conditions, geometry, material contrasts, stratification, and boundary shapes made it possible for energy to persist far longer than in the surroundings. Mountain ranges that recycled atmospheric wave energy, ice shelves that sustained low-frequency vibrations, and certain cavern systems that trapped sound all fit within this framework. The basin, however, stood out because of its extraordinary isolation. Its depth and shape, the arrangement of ridges at its flanks, the rheology of its sediments, and the properties of the overlying water column combined to create a system only weakly coupled to the rest of the ocean. Energy could enter, it could eventually leave, but the pathways were indirect and convoluted, and the timescales involved stretched far beyond any individual instrument's lifetime. The actual material remains of the ship, if they still existed, receded further into irrelevance as this view took hold. In conference talks and journal articles, the vessel was increasingly mentioned only as a historical perturbation, useful for dating when a particular resonance cycle had been strongly forced, but unimportant to understanding the basin's present behavior. The reinforced hold and its long-forgotten device had likely long since collapsed into the sedimentary matrix, their corrosion products indistinguishable from surrounding mineral grains. Whatever distinct mechanical properties they once contributed to the seabed had been blurred by compaction, bioturbation, and chemical alteration. The hull's acoustic personality, once sharp and geometric, had dissolved into the broader textural complexity of the basin floor. Yet every so often, in the data streams from hydrophones thousands of kilometers away, a pattern would appear that invited speculation. A cluster of pulses arriving with delays that matched, within the uncertainty of models, a path that included one or more reflections from the basin region, a frequency sweep whose curvature and time echoed the modeled response of a sediment-filled cavity driven near one of its resonant modes. A long, slow rise and fall in background noise level coincident with an episode of unusually strong stratification in the basin's deeper layers. None of these observations could be traced uniquely back to the vanished ship, but each served as a reminder that the event had been not just a loss, but an experiment, uncontrolled, unintended, and irreproducible, yet uniquely informative. At the same time, advances in three-dimensional seismic imaging and ocean bottom instrumentation produced increasingly detailed maps of the basin's subsurface structure. Long offset surveys using controlled low-frequency sources interpreted with powerful inversion algorithms, gradually resolved networks of high and low velocity zones beneath the seafloor. These zones corresponded to variations in sediment composition, porosity, and fluid content, as well as relic structures from past tectonic deformation. Among them, modelers identified regions that behaved in simulations as coupled resonant cavities, capable of exchanging energy with each other through narrow necks of more rigid material. When synthetic wave fields were propagated through these models, the patterns bore a strong resemblance to the mosaics of acoustic shadows and dimples observed in real sonar data. The basin, it became clear, could sustain a whole family of internal oscillations, some of which barely interacted with the water column at all, others of which projected energy efficiently into the overlying ocean when conditions aligned. Because these modes depended on factors that changed imperceptibly year to year: sediment compaction, slow fluid migration, tiny rearrangements of grain packs, they drifted not only in frequency but in spatial extent. A cavity that participated strongly in resonance during one decade might become acoustically decoupled in the next, while another region, previously quiet, might grow more responsive. In this way, the basin's voice evolved, its internal modes rearranging themselves in response to gradual geological processes. Whatever imprint the ship's resonance had left had to compete with these ever-shifting conditions. Over long enough intervals, the distinction between the basin's pre-existing modes and those shaped by the human-made perturbation became more a matter of narrative than of physics. The basin simply continued doing what its structure allowed: accepting, transforming, and releasing acoustic energy, according to the constraints of its changing form. In the broader practice of oceanography, the basin increasingly served as a cautionary example. It illustrated how easy it was to overinterpret or underinterpret ambiguous acoustic data. It showed that a seemingly straightforward target, a missing vessel of known size and composition, could become, under the right circumstances, effectively invisible without any exotic mechanisms, purely through the interaction of frequency, geometry, and time. Studies of the basin informed improvements in sonar signal processing, helping engineers design systems better able to distinguish true objects from coordinated environmental clutter. They also inspired conceptual work on how to avoid creating dangerous blind spots in future ocean monitoring architectures. Recognizing that some regions of the sea would never yield to simple scanning and might always harbor ambiguities that required patience and nuanced modeling rather than brute force sensing. As the decades stretched toward the end of the century, the basin's anomalies became less striking simply because the baseline understanding of the deep ocean grew richer. Features that had once been puzzling: persistent low-frequency tones, drifting bands of noise, localized navigation irregularities, could now be situated within a dense context of comparable phenomena observed elsewhere. New basins were found with similar, if not identical, behaviors. A few displayed even stronger resonance traits. Others showed coupled acoustic electromagnetic interactions or unusual sensitivity to distant atmospheric forcing. The original basin lost its uniqueness, becoming one case study among many in the emerging science of long-lived geophysical resonances. Still, when timelines were drawn of documented resonant events in the world ocean, one point near mid-century retained a special prominence: the period during which a cargo vessel, carrying a forgotten prototype, had crossed a particular set of coordinates under calm skies and disappeared from detection in a way that, although now more comprehensible in principle, remained impossible to reconstruct in detail. That crossing, and the convergence of conditions surrounding it, marked the moment when a human artifact had most clearly interacted with the deep ocean's capacity to store and reshape mechanical energy. It was, in that sense, a boundary between eras. Before it, the basin was a largely theoretical construct. Its internal complexity inferred only from scattered hints. After it, the basin became an object of focused study. Its quirks folded slowly into the expanding catalog of how the planet's hidden layers behave. Above the basin, ships continued to pass along their routes, guided by satellites, inertial systems, and redundant networks of sensors that mostly ignored whatever small perturbations the deep environment still imposed. Weather systems grew and decayed. Waves broke. Currents drifted. The sea surface remained indifferent to the elaborate structures below, its patterns governed by forces originating in the atmosphere and the rotation of the planet. Mariners crossing the region considered it no different from any other stretch of open water. There were no visible markers, no warning lights, no sudden changes in color to suggest that beneath them lay a volume of ocean and rock that, for a time, had extended the lifespan of a ship's mechanical whisper far beyond its own. In the depths, the basin's layered architecture continued to mature. Sediments thickened, cavities shifted, modes drifted. External disturbances came and went: storms, quakes, the noise of distant propellers, the calls of migrating whales, and each left tiny contributions to the evolving acoustic texture. The vanished vessel, once the focus of searches and reports, now persisted only as an influence, difficult to disentangle from everything else, its former distinctness diluted into a continuum of overlapping resonances. Whatever specific pulses its generator had contributed had long since cascaded through multiple transformations, emerging and re-emerging as attenuated, distorted fragments. Eventually, they became indistinguishable from the general murmur of the deep. By then, the story of the ship's loss had migrated almost entirely from operational concern to historical curiosity. Archives held its logs, its specifications, its freight manifests, and the investigations that followed its vanishing. Technical monographs referenced it as an early case of environmental acoustic masking. Students encountering the case in seminars often saw it as a parable about the limits of sensing, rather than as a mystery waiting to be solved. For the basin, this shift in perspective changed nothing. It remained what it always had been: a shaped volume of water and rock, moving slowly through its own cycles, indifferent to which particular sounds happened to excite its modes at any given time. And yet, in the logic of the physical world, nothing was truly erased. Energy once injected into a system followed its permitted pathways until dissipated into heat at scales too small to matter. Iron once forged into hull plates rearranged itself atom by atom as corrosion and burial progressed. Vibrations once traveling through the steel of a forgotten generator had, for a while, ridden the structures of the deep ocean and the sediments beneath it. And some trace of that interaction remained encoded in the precise distribution of grain orientations, pore shapes, and microscopic fractures scattered through the basin floor. No instrument could read such a record. No model could roll time backwards with sufficient fidelity to reconstruct it. But physically, it existed in the way that every past perturbation exists, not as a recoverable narrative, but as an infinitesimal influence folded invisibly into the state of things as they are now. From the surface, on a clear day, the region gave no hint of any of this. The horizon remained level, the waves small, the sky bright. The spot where the vessel had last been tracked looked like any other patch of ocean, its history concealed beneath kilometers of water. Only those who had spent years parsing faint traces in hydrophone data or stepping through layered models of pressure and density might have looked at such a scene and thought of what lay below: a slowly shifting labyrinth of strata and cavities within which the ocean occasionally rearranged its own sounds into patterns that could hide even something as large as a ship. With time, the basin story became less about a missing ship and more about the way the ocean itself handled memory. In the early decades after the disappearance, attention focused on what had been lost: a hull, a crew, a faint line on shipping registers that ended abruptly. Later, as instrumentation improved and models grew more sophisticated, the emphasis shifted toward what remained: the basin's persistent role as a place where signals behaved differently, where echoes bent and blurred, where the expected relationship between cause and effect in acoustic space refused to hold in simple ways. By the time global monitoring networks matured into dense, permanent systems, the question had quietly inverted. Instead of asking how a vessel could vanish in calm seas, researchers increasingly asked how any large object could ever be confidently said to have departed a region like that at all, given the ways in which energy and structure entangled there. In this new framing, the basin became one node in a broader web of interacting deep ocean environments. Long-term correlations between widely separated hydrophone arrays showed that changes in the basin's internal stratification subtly influenced propagation conditions thousands of kilometers away. A shift in its internal temperature gradient, for example, could alter the timing and apparent angle of arrival of low-frequency sounds recorded in another basin linked through the deep sound channel. Such effects were small, on the order of milliseconds or fractions of a decibel, but they were reproducible. To those who worked on such scales, the basin no longer looked like an isolated anomaly. It appeared instead as one element in a planetary-scale resonant network, its local quirks contributing to and being influenced by the global distribution of density, pressure, and acoustic pathways. Within the basin itself, high-resolution modeling began to explore scenarios that had not been attainable earlier. Researchers constructed digital analogs of the environment that included millions of discrete elements, stratified water layers with realistic microstructure, sediment columns with complex, depth-dependent mechanical properties, embedded cavities, and heterogeneities derived from inversion of seismic data. Into these simulations, they introduced synthetic sources resembling the long-gone resonance generator, low-frequency, broadband pulses, modulated in time in various ways, placed at different depths and positions. The results confirmed what had long been suspected but never demonstrated in such detail. Under certain configurations, the combination of source spectrum, basin stratification, and seabed structure produced interference patterns that rendered the source effectively undetectable from outside, even as its energy continued to circulate within. In some simulations, virtual ships vanished acoustically the moment their emissions synchronized with one of the basin's long-lived modes. Their direct return was absorbed into a pattern of standing waves that did not project efficiently into the surrounding ocean. To observers outside the modeled basin, the source's signature simply faded into the background noise, replaced by a vague increase in low-frequency fluctuation that did not localize cleanly. The analogies to the historical case were not perfect. The real crossing had involved external transmissions, not active emissions from the hull itself, but the underlying mechanism was similar. The capacity of the environment to capture and reroute acoustic energy could, under rare alignments, deprive external instruments of clear evidence that an emitter still occupied a given volume of water. These findings had practical ramifications. Naval planners and designers of civilian search systems alike had to reckon with the possibility that certain ocean regions could transiently behave as detection shadows, not because of any active countermeasures, but because the environment itself occasionally conspired to obscure targets. Protocols for lost vessel searches were revised to account for the existence of acoustically difficult basins. Efforts to validate disappearance locations using sonar alone were increasingly supplemented with alternative methods, including satellite-based surface sensing and careful analysis of drift patterns. While no other loss reproduced the specific features of the cargo ship's case, the mere recognition that such a combination of circumstances was possible changed how risk was understood. At the same time, the basin grew in importance as a natural laboratory for studying environmental resonance in its own right. Long-duration moorings were placed at multiple depths, their instruments recording pressure, temperature, current velocity, and sound over spans measured in years. Although funding priorities waxed and waned, enough continuity of observation was maintained that researchers could begin to draw robust statistical conclusions about the basin's behavior over climatic timescales. They found, for instance, that the intensity and frequency of anomalous acoustic bursts correlated with slow oscillations in large-scale circulation patterns, such as shifts in deep water formation rates in distant subpolar regions. When dense water masses produced at high latitudes eventually reached the basin along abyssal pathways, their slightly different temperature and salinity characteristics altered the internal structure enough to change which resonant modes were favored. In years following such arrivals, the basin's low-frequency output assumed slightly different spectral shapes, even in the absence of any obvious local disturbances. This sensitivity turned the basin into a kind of indirect recorder of the global deep ocean state. Just as tree rings and ice cores provide archives of past atmospheric conditions, the basin's evolving acoustic fingerprints came to be seen as an archive, not of specific events, but of the long-term background against which those events occurred. When modelers tuned their simulations to reproduce the observed patterns, they found that only certain histories of deep water flow and sediment compaction yielded the observed sequence of resonant shifts. In that sense, the basin's present-day murmurs contained, encoded in their detailed structure, constraints on how the ocean's interior must have changed over the preceding decades. In discussions of such work, the vanished ship occupied an ambiguous place. On the one hand, its disappearance continued to provide a concrete, human-scale hook on which to hang explanations of otherwise abstract processes. On the other hand, as the temporal horizon of analysis extended and the focus broadened, the event looked more and more like a small fluctuation superposed on a much larger set of patterns. It had been, in effect, a perturbation experiment with a single replication, conducted accidentally. The mechanical energy injected into the basin by the resonant interaction between hull, device, and environment did not differ fundamentally from that produced by a major storm front or by the calving of ice from a large glacier. It was distinctive only because it coincided with the failure of detection systems that humans happened to be operating nearby. That coincidence ensured that the ship's story would survive in records, but it did not grant it special status in the physical evolution of the basin. When researchers plotted the cumulative acoustic energy entering the basin from all sources, distant earthquakes, shipping, storms, marine life, and sporadic anthropogenic experiments, the contributions from the vanished vessel's crossing represented only a minuscule fraction. From the standpoint of the basin's internal modes, the ship's generator had provided one among many hundreds of nudges, each adding a tiny weight to certain oscillations, each helping to shape the detailed phase relationships that emerged later. The idea that the ship had caused the basin's subsequent anomalies was gradually replaced with the more modest notion that it had participated in them. Nevertheless, for those interested in the interplay between human technology and natural environments, the case remained instructive. It demonstrated that equipment designed under one set of assumptions, wartime acoustic experimentation, limited understanding of deep sound channels, narrow operational goals could, when relocated in time and context, produce effects that were not just unexpected, but perceptually meaningful in ways far removed from the original design. The resonance generator had not altered the basin's basic physics, but it had made those physics visible. First to the sonar operators who recorded the anomaly beneath the ship at the moment of disappearance, and later to generations of scientists who used the case as a starting point for broader inquiries. Outside the realm of specialist research, the basin attracted little attention. Shipping routes adjusted over the years in response to economic and political forces, sometimes passing closer to the region, sometimes farther away. Fishing activity remained sparse, less because of any recognized hazard, and more because the deep basin did not support the kinds of ecosystems favored by commercial fleets. Occasional popular accounts of strange seas or vanishing ships mentioned the case in passing, often embellishing it with details not supported by the record reports of mysterious lights, of sudden fog banks, of crew behavior inferred from scraps of routine radio traffic. These narratives rarely touched on the intricacies of layered sediments or deep sound channels. They focused instead on the gap in the historical record, the fact of a vessel leaving port and failing to arrive. In that sense, two parallel versions of the basin coexisted. One, sparse and dramatic, belonged to maritime lore, a quiet patch of ocean where a ship had vanished without a trace. The other, dense and technical, existed in the memory of data arrays and in the layered structures of scientific literature. A complex, evolving resonator whose interactions with a single vessel were just one episode in an ongoing exchange of energy between ocean, rock, and atmosphere. For most people, these versions never met. Only in the minds of a few who had studied both the raw records and the reconstructions did they occasionally intersect, producing a more holistic picture in which the mystery and the mechanics were facets of the same underlying reality. Physically, the basin continued to change. On geological timescales, even structures that seemed stable within a human lifetime were in flux. Slow subsidence altered the basin's overall depth. Episodic slips along deep faults changed the stress fields in the underlying crust. Volcanic outgassing, in distant mid-ocean ridges, by altering the chemistry and density of abyssal water masses, contributed indirectly to the basin's internal layering. None of these processes announced themselves at the surface. Even in the acoustic record, they manifested primarily as gradual shifts, slight adjustments in the distribution of resonant frequencies, changes in the relative strength of certain modes, alterations in the timing between observed bursts and the external events that had likely triggered them. If, at some vastly later time, a future observer could somehow reconstruct in full detail the distribution of pressure, density, and mechanical properties throughout the basin, and then roll that reconstruction backwards in a perfect inversion of all the processes that had acted upon it, the ghost of the ship's passage would be there. It would appear as a tiny departure from the state the basin would otherwise have held, a minutely different distribution of energy among its modes, a negligibly altered pattern of grain contacts in the sediment, a slightly different arrangement of microscopic fractures in certain pockets of rock, but no such inversion was possible. Entropy saw to that. Instead, all that remained was the forward trajectory, an environment that had absorbed countless perturbations, including one linked to a vessel whose loss had been documented and had blended them into the ongoing evolution of its own structure. From above, the view retained its deceptive simplicity. Satellite altimetry continued to show only a faint depression in sea surface height where the basin lay, the result of the slightly greater mass of deep water and dense rocks below. To imaging radar, the region's wave patterns differed little from those elsewhere under similar wind conditions. Clouds passed overhead, and weather systems traced their own logic, unconcerned with the subtleties of the deep. If, on a clear day, a ship steamed across the coordinates once associated with the vanished vessel, the crew would see nothing unusual. Instruments would function normally, except perhaps for a few brief and easily ignored fluctuations. The ocean would appear as it always did, a continuous, restless surface, opaque to the eyes of those who rarely considered what lay kilometers beneath their hull. Yet regardless of recognition, the deeper reality persisted. In that volume of water and rock, arranged just so by tectonics and time, acoustic energy continued to find long, circuitous paths, sometimes refusing to leave quickly when invited, sometimes reappearing where no obvious source remained, sometimes distorting the images formed by sensors that assumed simpler behavior. And somewhere within the unresolvable complexity of that behavior, there were still components infinitesimally weak now, hopelessly entangled with everything else that had once been part of the mechanical vibrations of a cargo vessel's hull, of frames and plates and braces shaking in response to a resonance generator built for a very different purpose in an earlier age. In that sense, the ship had never entirely left, not in any way that mattered for navigation or for the practicalities of the surface world, but in the strictly physical sense that its influence, once exerted, remained woven into the state of the environment that had absorbed it. The basin's present, layered over countless other contributions, still contained, in the smallest and least accessible details, the traces of that interaction. What was gone was not the effect, but the ability to separate it out, to point to any particular pattern, and say with certainty, this, here, is where the ship was. The basin's evolution entered an era so slow and so intricately partitioned across time that even long-term monitoring arrays struggled to capture its transitions in a coherent form. What had once been viewed as a single acoustic environment gradually revealed itself to be a set of interlocking subsystems, each operating on its own characteristic timescale, and each influencing the others through exchanges of pressure, sound, temperature, and mass. At the largest scale were the abyssal circulation loops broad, slow rivers of cold water moving through the global ocean, taking centuries to complete a circuit. These flows brought with them faint signatures of events far beyond the basin's local boundaries. Eddies shed from subpolar fronts, dissolved compounds from distant river outflows, even thin plumes of volcanic particulates vented from ridges thousands of miles away. These introduced subtle but real changes in density and chemistry that, when filtered through the basin's elaborate layering, produced shifts in the speed of sound and the fine structure of thermal boundaries. On top of these, smaller-scale processes played out. seasonal temperature fluctuations barely perceptible at depth, slow vertical migration of water masses driven by gradual shifts in surface cooling, the steady, almost imperceptible compaction of sediments that thickened the acoustic lensing structures beneath the seafloor, the occasional microseismic tremor that rearranged grains in local pockets of the crust. Individually, each process seemed inconsequential. Collectively, over decades and centuries, they shaped an interior world of overlapping gradients, within which sound traveled not along a single path, but through a labyrinth of temporary corridors, branching, recombining, and diffusing as the underlying geometry changed. These dynamics were invisible to surface observers. Even the most advanced multi-frequency sonar systems could only hint at them. The deeper one looked, the more layered and ambiguous the returns became, until the noise floor swallowed the difference between a genuine structure and a transient rearrangement caused by nothing more than subtle changes in water density. In certain epochs, researchers noticed that the basin's internal walls of stratification aligned for years at a time, producing periods when long-range acoustic propagation through the region became oddly stable. Sonar beams that once scattered unpredictably began to follow nearly identical paths across successive surveys, creating the fleeting illusion that the basin had become simpler. But such stability never lasted. Sooner or later, a shift in circulation would tilt the gradients again, and the previously coherent channels would fragment into a patchwork of diffuse, overlapping routes, returning the basin to its habitual unpredictability. What made this complexity profound was not merely its spatial variation, but its ability to store history. Unlike air, where temperature and density equalize rapidly, the deep ocean maintained layers that retained their identity for decades. A parcel of water that sank in the subpolar North Atlantic could take half a century to reach the basin. During that journey, its temperature and salinity preserved faint information about the conditions under which it formed. When it finally descended into the basin's interior, it joined existing layers, subtly altering their properties. These changes in turn reshaped the acoustic environment, modifying which resonant modes were most active and how long they persisted. Sediments, too, carried their own record, compacted into strata of varying density that responded differently to passing vibrations. A strong storm in the distant past, its energy transmitted into the deep by long-traveling infrasonic waves, might have altered the microstructure of certain pockets by rearranging grains or shifting fluid content. Over years, these microscopic reconfigurations hardened into features that participated in the basin's acoustic structure, even though their origins were lost to time. In such a world, the notion of a single event leaving a permanent mark was not far-fetched. Human activity, though minuscule against geological forces, could feed energy into the basin in ways that natural processes rarely did. Sharply tuned, highly coherent, arrayed across narrow bandwidths. These qualities made the experimental resonance generator, carried by the vanished cargo vessel, unusual among the basin's many perturbations. At the time of its accidental reactivation, the basin had been in a rare configuration where its internal modes aligned closely with the device's low-frequency output. The result was an efficient coupling, a situation in which even small amounts of energy could be captured and stored. Although the generator itself had long since corroded into silence, and the vessel's frame had ceased vibrating decades ago, the energy it introduced had participated in a cascade of interactions that propagated through water, sediments, and rock. Modern analysis, though powerful, could not perfectly reverse this chain. But researchers employing sophisticated inverse methods, mathematical techniques once used to infer the properties of stars and distant planets, attempted to reconstruct the basin's acoustic history based on present-day observations. These reconstructions did not aim to resurrect the vanished ship's signature. Instead, they sought to understand how the basin's modes had evolved and which perturbations must have influenced them. In some models, the basin's resonant structures exhibited discontinuities at times, corresponding roughly to the mid-century period when the ship disappeared. These discontinuities manifested as shifts in mode amplitude, changes in attenuation rates, or the sudden appearance of a previously dormant spectral component. Yet such reconstructions were inherently imprecise, clouded by the basin's continuing evolution. They suggested influence without being able to distinguish whether the ship had been the cause or simply one participant in a broader convergence of natural factors. As these investigations advanced, interest turned toward the possibility of mapping the basin's deepest structures with techniques that did not rely solely on sound. High-energy neutrino detectors placed on the seafloor, originally intended for fundamental physics experiments, offered faint hints of density contrasts far below the reach of conventional sensors. Their readings, though coarse, implied a subsurface arrangement even more heterogeneous than earlier models had assumed. Regions of unexpectedly low density alternated with compact blocks of mineral-laden sediment, forming a hidden quilt of materials that influenced sound propagation in ways that no previous mapping had captured. Satellite gravimetry, measuring minute deviations in Earth's gravitational field, offered corroborating evidence. The basin's mass distribution showed anomalies consistent with large buried cavities or hardened structures. Neither technique could resolve objects on the scale of a ship's hull, but together they painted a clearer picture of why the basin remained such an elusive environment, one where even large objects, if enveloped by sediment and surrounded by complex geophysical features, could vanish without violating any physical law. With such tools, researchers occasionally revisited the question of whether the vessel might still be accessible to detection. Some proposed deploying arrays of active acoustic sources specifically designed to excite the basin's internal modes, then analyzing the reflected patterns to identify deviations caused by solid objects. But simulations showed that such efforts would always be confounded by the basin's layered architecture. Energy introduced by the sources would scatter through too many channels, their returns entwined with the echoes of thousands of unrelated structures. Others advocated for deep drilling, imagining that a carefully chosen coring site might recover remnants of the ship. Yet the depths involved, combined with the low probability of hitting the precise location, rendered this approach impractical. Eventually, consensus formed that while the basin's physical contents could be modeled statistically, its individual features, especially something as small as a buried vessel, would remain inaccessible. In the end, what persisted most strongly were the patterns, not the objects. The basin continued to emit faint acoustic irregularities, detectable across long-range networks whenever its internal layers aligned. These emissions no longer resembled the harmonics once tentatively linked to the vanished ship. Instead, they formed part of the basin's ongoing rhythm, a shifting distribution of energy that, while influenced by countless past events, belonged fully to the basin itself. The oceanographers who studied these patterns did not expect them to offer answers about the disappearance. They saw them instead as evidence of a system with memory writ into its structure, one that absorbed and reinterpreted disturbances across centuries. By the time these conclusions solidified, the vessel's story had transitioned almost entirely into history. Maritime databases recorded its departure and its failure to arrive. Weather logs confirmed the calm conditions that surrounded the event. Memoirs from crew members of nearby vessels mentioned nothing unusual, only the striking stillness of the sea that day. The search reports that followed documented a sequence of reasonable assumptions, none of which had anticipated the basin's complexities. Later analyses placed the loss within a broader set of cases where environmental factors interfered with detection, though none matched this one in intricacy or ambiguity. In the basin itself, life continued in quiet cycles. Deep-sea organisms migrated through its layers, sensing subtle gradients that guided their movements. Planktonic species rose and fell with tidal rhythms, their presence creating faint acoustic scatter that added shimmer to the background noise field. Occasionally, large marine animals ventured near the basin's edge, their low-frequency calls interacting briefly with the internal modes before dissipating. These biological contributions layered onto the geological and physical ones, each adding its own texture to the basin's acoustic personality. Centuries hence, long after the machinery that once hummed within the ship's reinforced chamber had dissolved into sediment, after the vessel's steel frames had become indistinguishable from the mineral deposits enclosing them, the basin would still be shaping and reshaping itself. It would still be modulating the sounds that passed through it, still absorbing and releasing energy according to the constraints of its evolving architecture. The lost vessel, reduced to atoms and influences, would exist only as a tiny and irretrievable component of that architecture, folded into the basin's memory so completely that no trace of its identity remained. To the ocean, this was not loss, but continuity. A structure had entered, vibrated, and dissolved. The energy it contributed had long been redistributed. The patterns it helped to excite had diffused through countless interactions. What had once been a distinct object became part of the environment itself, and far above, the surface retained its simple facade. Ships crossed in calm weather, unaware of the immense layered complexity beneath them. Instruments measured wind and waves, oblivious to the deep rhythms that occasionally sent faint whispers into the global sound channel. The basin lay hidden, quiet, and indifferent, its vast interior shaped over millennia, its memory etched into gradients of density and sediment, its stories unknowable and full, but perpetually present in the physics of the deep. The vessel that once vanished there did not endure in form or echo. It endured only in the impossibility of recovering it, a reminder that the ocean, even in its calmest moments, holds dimensions of depth and time far beyond the reach of certainty. As the basin's evolution carried on through centuries of incremental rearrangement, it entered a state best understood not as stability, but as persistent transition. Each layer of water, each tier of sediment, each mineral pocket within the underlying crust adjusted according to forces that acted on scales far exceeding human timescales: the slow drift of tectonic plates, the diffusion of heat from the planet's interior, the migration of abyssal currents, and the steady rain of particulate matter descending from the upper ocean. No boundary remained fixed. No profile persisted indefinitely. What might seem, over decades of observation, like a consistent structural pattern, was merely a phase in an unending sequence of subtle transformations. In this evolving matrix, acoustic properties altered continuously, not in abrupt shifts, but in smooth gradients that accumulated significance only when examined across centuries. The resonant cavities beneath the seabed changed shape as sediments compacted and mineral deposits crystallized or dissolved. Boundaries that once reflected sound with sharp efficiency grew diffuse. Others, once negligible, became strongly refractive. Though these adjustments unfolded too slowly for any single generation to fully perceive, their combined effect was profound. The basin's character, as understood through sound, gradually transformed into something distinctly different from what it had been in the mid-century years surrounding the vessel's disappearance. The basin's place within the global ocean also changed. As continents drifted and ocean basins deepened in barely measurable increments, the region's connection to the deep sound channel shifted in subtle ways. Changes in the Southern Ocean circulation altered the origin and composition of water masses that eventually flowed into the basin. Meanwhile, atmospheric warming modified stratification patterns in the upper ocean, altering the density gradients that dictated how sound entered and exited the deep layers. These transformations brought distant histories into contact with the basin, carrying with them the acoustic fingerprints of faraway events. Powerful storm systems in the high latitude sent long wavelength infrasound pulses penetrating deep into the global ocean, some of which reached the basin with enough coherence to interact with its internal modes. Underwater landslides in remote trenches produced low-frequency shock waves that diffused along the deep channel, eventually intersecting the basin's layered structure. Even distant ice shelf collapses, far removed in geography and context, generated pressure pulses that, after traveling for months or years, arrived as faint tremors capable of perturbing the basin's evolving acoustic spectrum. Each of these interactions left minute fingerprints. They altered the amplitude of long-lived resonances by negligible degrees. They shifted the relative timing of overlapping modes by fractions of a second. They deposited tiny increments of energy into pockets where the basin stored sound for extended periods. In isolation, such changes meant nothing. But taken together, over the span of centuries, they drove the basin through cycles of acoustic reconfiguration too intricate for surface observers to reconstruct. The basin, though influenced by global events, did not merely receive these contributions passively. Its internal architecture reshaped them, filtering and transforming the incoming signals according to its own evolving geometry. In doing so, it continued to produce anomalies, detectable across the world ocean, faint drifting bands of noise, quasi-periodic bursts, distortions in long-range reception paths. These anomalies, when mapped across dozens of unrelated monitoring projects, formed a coherent pattern originating from the same region, a pattern of influence so dispersed and weak that only large-scale correlation revealed it, but so persistent that its presence across centuries could not be dismissed as coincidence. During these same epochs, oceanographers and geophysicists continued refining their tools. By the time global monitoring systems had achieved near complete coverage of the deep ocean, the basin's anomalies had become one of the most thoroughly documented long-term acoustic phenomena on Earth. Yet the documentary richness yielded no corresponding increase in interpretive certainty. Data accumulated faster than theory could accommodate it. High-resolution benthic seismographs recorded faint, ultra-low frequency tremors that originated within the basin but matched no known pattern of microseismic activity. Sensitive thermistors revealed temperature shifts within deep layers that did not fit expected diffusion profiles. Pressure sensors registered oscillations that correlated with neither tides nor seismic events nor internal waves, but instead demonstrated a slow drift reminiscent of a resonant system responding to distant forcing. In each case, the basin's internal complexity overwhelmed attempts at resolution. Even with centuries of measurements, researchers could not extract a single consistent mechanism to explain every anomaly. It was in this context that the fate of the vanished ship gradually transitioned from a concrete historical question into a theoretical abstraction. Early studies had sought the hull as a discrete object, believing it could be found if the correct tools were applied. Later studies sought its remnants as a set of materials, corroded metal, compacted sediment, structural fragments, assuming that some trace still existed that could be distinguished from surrounding geology. Still, later studies considered its influence in terms of resonance patterns, supposing the ship had contributed energy that the basin stored and redistributed. But by the time oceanographic science reached its mature global phase, the ship no longer fit neatly into any framework. It became, instead, a reference point for understanding the limits of detection. Its disappearance represented the confluence of an object, an environment, and a moment in which human sensory systems lacked the dimensionality required to perceive the full state of the world. Modelers eventually demonstrated that, given the basin's evolving structure, there existed infinitely many configurations consistent with the historical measurements taken during the search. Some of these configurations involved the vessel descending intact, settling on the seabed, and gradually being buried under sediment. Others involved the vessel fracturing, its pieces dispersed across a wide radius by slow turbidity flows that occurred unnoticed. Still others involved the ship never reaching the seabed at all, instead becoming suspended within dense layers of sediment-charged water, its acoustic signature masked from below by scattering and from above by stratification. None of these scenarios negated the possibility that the vessel existed in some form within the basin, but none allowed for decisive confirmation either. The environmental degrees of freedom far outnumbered the constraints imposed by the data. As centuries passed, the basin underwent transformations more profound than any seen in the initial decades following the disappearance. Sediment columns thickened until their deepest layers behaved less like loose accumulations and more like metamorphosed rock. Under increasing pressure, the sediments compacted into laminated structures that modified seismic and acoustic propagation in ways once reserved for solid geology. Mineral deposits crystallized into intricate networks that further diffused sound. Some cavities collapsed under the weight of overburden. Others expanded slowly as pore fluids migrated and reshaped the underlying strata. These processes altered the basin's reflective properties so dramatically that the acoustic landscape of the far future bore little resemblance to that recorded in the centuries following the ship's last known position. The ship, if any parts remained intact at all, would have become indistinguishable from these geological features. Any sharp geometric contour would have been erased by corrosion. Any surviving internal frame would have been compacted into mineral-encrusted irregularities indistinguishable from natural concretions. Even the reinforced hold, once the unique core of the vessel's acoustic character, would have been absorbed into the broader sediment structure, its materials chemically transformed, its cavities filled by deposits, its outline softened until no pulse, not even the lowest frequency seismic waves could differentiate it from the surrounding environment. In this way, the vessel became not merely lost but fully assimilated into the basin's evolution. It ceased to be an external object interacting with its environment and became part of that environment itself. On the surface, nothing reflected these developments. The region remained visually serene, a calm expanse of ocean framed by shifting weather, occasionally crossed by ships whose crews had no knowledge of the basin beneath them. The deep processes shaping the basin, geological compaction, stratification, acoustic resonance, were so slow and so subtle that they created no visible marks. Even the ocean's color remained unchanged, shaped more by surface scattering and biological activity than by anything happening kilometers below. Only when sensitive long-range hydrophones recorded faint anomalies did the basin assert its presence in human perception. And even then, those anomalies were so diffuse, so integrated into the global fabric of deep ocean noise, that only specialists recognized their signature. In the end, the basin's story and the vessel's place within it became inseparable from the broader narrative of Earth's deep interior. The ship's disappearance was no longer seen as an anomaly or a mystery, but as a case study in how environments of enormous complexity can exceed the dimensional reach of human observation. The basin represented one such environment, a dynamic archive of pressure, density, heat, and vibration, evolving continuously yet silently, indifferent to the events it absorbed. Its memory, expressed through sound and structure, extended far beyond the lifespan of any single artifact. The ship's final presence in the basin persisted not as an identifiable trace, but as a physical contribution to the conditions that followed. And so the ocean moved into ever more distant epochs, its internal landscapes shifting, its resonances drifting, its hidden architectures folding and unfolding in ways that no surface world could witness. The vessel's passage, once a point of focus, dissolved into anonymity, its existence preserved only in the abstract physics of a system too large, too deep, and too slow for any complete comprehension. The basin remained, evolving without end, bearing within it the faint, irrecoverable imprint of everything that had ever entered its depths, the vessel included. As millennia accumulated and the oceanic landscape passed through cycles of climatic rearrangement, the basin persisted as a domain defined not by stability, but by transformation distributed across magnitudes of time no single epoch could contain. What had once been a moderately deep depression in the seafloor evolved, layer by layer, into something far more complex, a composite archive of processes that spanned entire geological eras. The sediment layers that had once lain loosely stacked became compressed into lithified bands, each encoding the particulate memory of a bygone surface world. Diatomaceous silts, volcanic ash deposits, mineral dust from long-vanished deserts, microscopic shells from species extinct for ages, all of it compacted into strata of increasing rigidity. Over unimaginable spans, these layers bent under tectonic stress, forming gentle folds that altered the basin's geometry in subtle but acoustically significant ways. The walls of these folds acted like slow-moving boundaries. Their curvature redirected deep-traveling pulses along new trajectories, transforming the basin yet again into a different acoustic entity. What centuries of oceanographers had once mapped as a single coherent depression now revealed itself, at geological scale, as a migrating form, an entity not fixed in place but slowly shifting, its deepest contours moving outward or inward, depending on pressures from beneath. Below the sediment, tectonic processes progressed with patient inevitability. The basaltic crust that supported the basin continued to cool and contract, creating microfractures that over time filled with mineral-rich fluids rising from deeper layers. These infillings changed the mechanical impedance of the crust in small increments, altering how pressure waves passed from water into rock and back again. Some fractures sealed, others expanded. Periodic convection of mantle heat beneath the region caused slight uplifts in the seafloor, not enough to be perceptible in human timescales, but immense when viewed across 1,000 generations. These warpings, though measured in centimeters per millennium, reconfigured the basin's ability to trap sound, forming new resonant chambers and dissolving old ones. What acousticians once modeled as a fixed structure turned out to be an evolving labyrinth, whose pathways were governed by cycles so long that no measurement campaign, no matter how sustained, could ever capture the full scope of change. At the same time, the ocean above the basin underwent transformations shaped by ice ages, interglacial warm periods, and shifts in the distribution of global currents. During cold periods, dense water formed in vast quantities at high latitudes, driving powerful flows into the deep ocean that carried with them different chemical signatures, higher oxygen content, reduced particulate matter, altered salinity. These water masses, upon entering the basin, behaved differently from their predecessors. Some formed sharply stratified layers that acted as temporary acoustic mirrors. Others diffused more gradually, dissolving boundaries that earlier epochs had reinforced. In warm intervals, surface productivity surged in some regions and collapsed in others, altering the rain of organic matter that fed the sediment columns. Each climatic phase inscribed its own signature on the basin, not as a single event, but as a slow rewriting of the environmental preconditions for resonance. Through all these transformations, the location where the cargo vessel once vanished remained suspended in the deeper continuum of the basin's identity. By now, the ship's physical presence, if any remnants survived, had been wholly absorbed into the geological fabric. The metals that once formed its hull had either dissolved into ions or become embedded within mineral concretions. Structural elements had disarticulated long before even the earliest cycles of deep sediment compaction had begun. What little remained of the vessel was indistinguishable from the surrounding matrix, its atoms redistributed into forms that bore no structural relation to the frame they once composed. The reinforced compartment that had once housed the experimental acoustic device had collapsed, infilled, compressed, and lithified to the point where no difference existed between its contours and the broader sedimentary block. And yet, though the vessel had no surviving shape, its influence on the basin's acoustic evolution persisted in ways that no longer resembled memory, but rather inheritance. The resonance it had helped excite, the disturbances it had introduced into a system primed for long-lived oscillation, had been absorbed and redistributed across too many cycles to identify. Some small portion of the energy it released had likely entered deep sediment pores and caused infinitesimal rearrangements at scales so small no model could track them. Other portions had traveled along refractive pathways into deeper channels, becoming entangled with pulses generated by tectonic shifts or distant landslides. These entanglements, though attenuated beyond recognition, contributed in theory to the statistical texture of noise fields that centuries of hydrophones recorded. It was not that the ship's resonance remained so much as that it had been folded into the basin's evolving structure. What persisted was not a signature, but participation. Over even longer horizons, tens of thousands of years, the basin's identity changed again. Ocean basins deepened as plates moved, new ridges formed, others subducted. The deep sound channel itself migrated vertically, responding to large-scale climatic shifts that altered the thermal gradient of the world ocean. At times, the channel dipped closer to the basin, enhancing its ability to inject anomalous signals into global circulation. At other times, it rose away, isolating the basin's acoustic behavior in a lower stratum cut off from long-range propagation. Meanwhile, ice ages advanced and retreated, lowering and raising global sea levels by hundreds of meters. During low stands, sediment transport intensified as continental shelves were exposed and rivers carved new routes into the sea. Massive plumes of suspended particles drifted into deep basins, altering their chemistry and adding new layers to their sediment archives. During high stands, warm stratified waters suppressed mixing, thickening the density gradients that shaped sound pathways. Throughout these epochs, the basin did not retain a single stable identity. Rather, it passed through sequences of acoustic personalities, periods when its deepest modes favored long, low-frequency oscillations, periods when the structure became too diffuse to support strong resonance, periods when internal boundaries aligned in such a way that faint signals could persist for centuries, periods when all stored energy bled away quickly due to increased mixing. In each phase, the basin interacted differently with the global ocean, sometimes serving as a faint but measurable node of influence, sometimes disappearing entirely into the background of deep-sea noise. Human presence, by contrast, faded. The age of hydrophones and long-range monitoring networks came and went. The instruments that once listened to the basin corroded, collapsed, were buried in sediment, or were destroyed by tectonic shifts they had no capacity to detect. Their data survived only in archives that themselves succumbed to the entropy of centuries lost in migrations of civilizations, failures of storage, disruptions of continuity. The basin remained, indifferent to the fate of the species that once tried to understand it. Its long cycles played out in the dark, untouched by any observer. Eventually, even the memory of the vanished vessel disappeared from human culture. Records were lost or obscured by time. Languages changed. Knowledge domains rose and fell. The precise coordinates of the ship's final transmission dissolved into obscurity, and only those physical transformations that the basin itself underwent endured. If the ship ever had a story beyond its physical dissolution, the ocean absorbed it, not symbolically, but literally, through pressure, temperature, sedimentation, and the quiet mechanics of deepwater resonance. Many tens of thousands of years later, if some descendant intelligence, human or otherwise, attempted to probe the basin's interior, it would encounter a structure bearing no resemblance to the one known in earlier ages. It would detect strata hardened into rock, cavities compressed into narrow seams, mineral structures grown thick and irregular, and deep acoustic channels reorganized into new geometries. It would find no object that matched the mass, shape, or composition of a mid-20th century cargo vessel. It might detect anomalies, small pockets of density that deviated from their surroundings, but these would be products of geological development, uninterpretable without the historical context long since erased. No tool, no matter how advanced, could reconstruct from these remnants the vessel's contours or the mechanics of its disappearance. The ocean, over such spans, preserves nothing except the processes that continually rewrite it. The basin, once the stage for a vanishing, evolved into something larger than any event it had hosted, its memory encoded not in objects, but in gradients, boundaries, and the physics of deep water and stone. What once puzzled observers became assimilated into the untraceable background of natural processes too vast to catalog. And so the vessel's fate, once a mystery, later an academic puzzle, later still a footnote, became finally part of the anonymous mass of the Earth's deep interior, dissolved into cycles far older and far longer than the ship or the people who built it. It had not merely sunk, it had been absorbed into the ongoing transformation of the planet itself. In the most literal sense, nothing was left to find. Only the ocean endured. Across spans so long they ceased to resemble time in any human sense, the basin continued its slow metamorphosis, reshaping itself under pressures both internal and external. Each new layer of sediment, each incremental shift in density, each microscopic rearrangement of minerals contributed to an evolving interior architecture that bore no resemblance to what had existed during the ship's final passage all those thousands of years earlier. The environmental memory of the event, once faintly visible in acoustic irregularities, then diffused into layers of new modes and patterns, dissipated into a continuum of interactions, too complex to attribute to any singular origin. What had begun as an observable anomaly in a mid-century sonar recording became, over time, indistinguishable from the basin's own inherent variability, absorbed into its physiology the way heat dissipates into air, retaining no boundary between source and environment. Changes at planetary scale eventually exerted deeper influence, long after human civilization's archived observations had vanished under the weight of lost languages, continental reshapings, and the progressive erasure of technological epochs. The Earth's crust beneath the basin entered a phase of slow uplift. Regions of seafloor basin rose by imperceptible degrees, altering the paths by which abyssal waters circulated around them. Sediment layers that had once drifted downward in steady columns now shifted sideways under gravitational readjustments, bending into new shapes, compressing along fresh lines of stress. Subtle intrusions of molten material infiltrated deep fractures as the crust adjusted to changes in mantle convection, cooling into dense veins of rock that redirected seismic and acoustic energy along unfamiliar vectors. These tectonic processes, acting over tens of thousands of generations, altered the basin far more dramatically than the modest depositional shifts of earlier ages. What had once been an open depression became, gradually, a complex of ridges and folds impossible to delineate without reconstructing immense stretches of lost geological time. The basin's acoustic character drifted along with its changing shape. Layers that once trapped energy dissolved into turbulence. New boundaries formed, where rising mineral structures pressed into compacted sediments. The deep sound channel, migrating with climatic cycles and the reshaping of the ocean's temperature-salinity structure, passed above or below the basin at different stages, alternately linking it to far-off regions and isolating it within quieter pockets of deep water. Its ability to trap, transform, and re-emit long-lived frequencies changed accordingly. During some epochs, the basin became almost acoustically dormant. During others, it produced persistent tremors that spread through the abyss, like the faint residue of forgotten events. Tremors that no listener, even if one existed, could unravel into individual contributions. By the time the basin entered its final recognizable form, the traces of the vanished vessel had become indistinguishable, not merely in detail, but in principle. The difference between the ship's matter and the basin's matter no longer existed. The components of its hull, its bulkheads, its fittings, had long since been redistributed into mineral matrices, whose chemical identities bore no imprint of their origin. The reinforced compartment, once the vessel's most distinctive structure, had been dismantled atom by the chemistry of seawater, gravity-driven compaction, and geological reprocessing. Its materials woven into sedimentary stone or carried away in solution into water masses that underwent their own cycles of transformation. Nothing remained in a form that could be called an object. Nothing remained in a form that could be said to belong to a vessel, or to an event, or to any discrete human artifact. The basin evolved into an entirely different geological province. Over immensely long periods, plate boundaries shifted, and what had once been deep ocean floor approached a zone of subduction. Portions of the basin's lower layers sank slowly into the Earth's interior, where they encountered temperatures and pressures that erased all structural memory. Minerals melted, iron recombined, carbonates dissociated, silicates reformed into crystalline lattices, indifferent to the histories carried by their constituent elements. In these conditions, even the notion of remains ceased to hold meaning. The matter that once formed the ship's hull, the machinery inside it, the reinforced compartment, and every trace of its physical presence melted into the convective mantle, becoming part of flows that ascended and descended in cycles hundreds of millions of years long. The ship's final legacy was reduced to particles indistinguishable from the rest of the planet's interior flux. Because the ocean itself was not static on geological scales, the basin too succumbed to planetary change. Eventually, whether by subduction, uplift, or the closure of ocean basins during continental convergence, the region that once held the disappearing vessel ceased to be ocean at all. Sediments that once absorbed acoustic energy lay trapped between colliding landmasses, folded into mountain roots, or thrust upward into rocks that would someday form ranges higher than any ocean ridge. What had once been abyssal depths became buried beneath kilometers of crust or raised into the light of a new world. In either case, no future observer, no matter how advanced their science, could have traced any remaining structure to an event that had taken place in a vanished ocean, on a vanished seafloor, within a vanished basin that no longer had any physical correspondence to the shapes of the Earth's surface. Thus, the tale of the vanished vessel reached its ultimate conclusion. It did not end with discovery or resolution, nor with contradiction or closure. It ended with dissolution, not simply of the ship itself, but of the environment that once held it. The basin absorbed the ship's presence, then evolved beyond recognition, then disappeared into deeper planetary processes that erased its identity altogether. The ocean kept no lasting record, only temporary patterns that faded as the physical substrate beneath them transformed. For a time, the vessel's loss had been an unsolved event. Later it became a scientific puzzle, then an academic reference, then a historical footnote drifting away in the tide of eras. Far later it became nothing at all, not through neglect, but through the absolute continuity of natural change, a process in which every structure is eventually rewritten. In the end, the vessel did not lie. Forgotten beneath the sea, it did not lie anywhere. What had once been a ship became part of the deep ocean's shifting memory, and then part of the Earth's interior, and then part of the cycles that shape continents and oceans across the life of the planet. Its disappearance was not an anomaly, but a transition, a brief intersection between human time and geological time, visible only in the fleeting interval when humans were capable of noticing it. Long after the last surface waves passed above the coordinates where it once sailed, long after the ocean itself transformed beyond recognition, the vessel's story reached the final state shared by all things shaped by the Earth.
We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next, your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.